Okay, so this is excerpts from a book that I wrote a couple of years ago, and I'm keeping updated. It's called A New Paradigm for the Universe. I've been working on this for about 20 years, and I finally think it's more or less complete. And I'm really trying to get people to take some interest in it. So I'm hoping you will. Okay, so I put it everywhere. So these are the coordinates. You don't have to worry about the details here. You go to the archive and just look for me or for the title, A New Paradigm for the Universe. It should come up. And there's a little bit about me in case you want to know. I'm Professor Emeritus at the University of Warwick, taught all over the place, and I've done 50 years of lecturing, written papers all over the place. Maybe I'd be more famous if I'd stuck in one place. Anyway, whether that's true or not, I started taking interest in cosmology in 2000 and published a very big foray on the archive preprint server in 2003, which is the same, which is why the archive one is 2003. But there were lots of holes then, and I'm gradually filling them. For the past 10 years, I've got a very good collaboration with Robert Mackay, who's an extremely good applied mathematician at the University of Warwick, who understands a lot of pure mathematics. And there's a lot of pure mathematics in this theory, and this is one of the problems, I think. Anyway, we've collaborated on redshift, gamma ray bursts, and natural observer fields, and now I think it's ready, and I'm hoping to get it out. So if I die, you can send the book all over the place. Okay, so let's start. Cosmology is the study of the universe in the large. It's a topic which arouses a great deal of public interest, with serious articles both in the scientific press and in major newspapers, with many of the theories and concepts, for example, the Big Bang and black holes, discussed often in great depth. The observations that support these discussions use sophisticated and expensive machinery, both on the Earth, for example, the LIGO equipment used to detect gravitational waves, and in orbit around the Earth, the Hubble telescope. It's a very, very big operation. Lots and lots of government money. So it's important that it's properly founded, and I don't believe it is. There's a consensus for the theoretical framework supporting and interpreting these observations, and that's known as the Standard Model. It starts with the Big Bang and expands from there to fill the entire visible universe. The image that the subject presents is of a complete and full theory that, with a few minor unsolved problems, explains all the observations that we have. This image is, like many images, completely false. There are huge problems with the Standard Model, some of which will be discussed shortly. The aim of the book is to present an alternative model which avoids the most glaring of these problems. The models complete an outline with several topics covered in full detail, including the dynamics of galaxies and the nature of quasars. Okay, so let's look at the problems with the Standard Model. There are two major philosophical problems, and I think philosophy is very important. If you don't get the philosophy right, then you don't get the subject right. The first problem is the Mach's principle. The Standard Model is based on Einstein's theory of general relativity, which I often call EGR, and it doesn't satisfy Mach's principle in general. You can have space without anything in it. De Sitter space, that's what was found first, and we'll come back to that later probably. Anyway, the Mach's principle centers around the philosophically compelling idea that the concept of acceleration or rotation must be connected to the main distant mass of matter in the universe. Rotation is the simplest thing to think about. An observer can tell that he's rotating without leaving his closed windowless spaceship, because there are forces that he experiences, for example, Coriolis force, he does not experience if he's not rotating. But what possible difference is there between him rotating and him being still with the universe rotating around him? So the conclusion of this kind of thinking is that the forces he experiences are due to some mysterious effect of the rotation of the universe around him. These considerations have been passed into general circulation as Mach's principle, which is usually summarized as saying the local concept of inertial frame a frame in which there's no acceleration or rotation, is correlated with the distribution of motion of all the matter in the universe. Any theory which aims to accurately describe the universe must have such a property in some form. Einstein's general relativity does not. The second problem, again I think philosophically compelling, is the principle known as the Copernican or Cosmological Principle. This is the principle that no particular location should be special. There's no center to the universe, no fingers of God. This should also be true of time as well as space. There should be no special times. We should not live in a special time any more than we live in a special place. This space-time non-speciality principle will be called the perfect Copernican principle, PCP, which can also be read as the perfect cosmological principle. Obviously, the standard model, the current consensus model, does not satisfy this principle because it starts with a very special event at a very special time, the Big Bang. Well, the two philosophical problems addressed in the book, but not in this talk. What will be addressed, though, are two other major problems. The first is the so-called dark matter problem, and this is widely recognized. Sorry about that. And this is widely recognized as a major problem. Whilst the second, the arc problem, is not recognized, but it ought to be. The dark matter problem arises from the observed rotation curve for galaxies and is covered in the next section. This is the introduction. While the arc problem concerns the nature of quasars and discussed in the following section. Both problems are addressed in the new paradigm by using a simple and widely ignored relativistic effect, namely the dragging of inertial frames, inertial drag, or ID for short. As a bonus to solving the rotation curve problem, you get a good model for the spiral structure of galaxies. I don't think time's going to permit today because we wasted so much at the beginning, but if time permits, then I'll talk about the new model for the universe based on de Sitter space after all that. Okay, so it's time to get some actual cosmology up. Here's some lovely pictures coming up. This is M51, one of the most beautiful spiral galaxies around. I think it's a Hubble picture. This is M101, not quite so beautiful, but still very dramatic. This is M83 or Southern Pinwheel, going the other way. Okay, so spiral galaxies are surely the most beautiful objects in the universe, and it comes as a shock to find there's no proper theory for their structure in current cosmology. You'd have thought it would be trumpeted everywhere that we don't understand galaxies, but it just gets ignored. They just concentrate on the Big Bang, on inflation, on the cosmic microwave background, and they get all sorts of wonderful stuff, but they ignore the things that's right under their nose anyway. I'm chatting. The main problem arises from the assumption that stars move on roughly circular orbits. In order to maintain a spiral structure stably over several revolutions, with stars moving on circular orbits, it's necessary for the tangential velocity to be roughly proportional to the distance to the center. In other words, that it's rotating like a plate, which means that the rotation curve, that's the graph of tangential velocity against distance from the center, is miles off from the one that's actually observed. What's actually observed is a straight line through the origin, so it's plate-like rotation near the middle, and then it settles down to be the tangential velocity is constant. It's asymptotically constant. Okay, and anyway, so the problem, because of that, they don't think that what they're pretending is that spiral structure isn't real. What they're saying is that that the spiral arms are not real things, but virtual. And the conventional cosmology proposes they're in fact standing waves or density waves. Although standing waves or density waves could give plausible structure, spirals, sorry, I'm getting tongue-tied. The nature of the arms in real galaxies does not fit at all. Real arms are composed of a spiral curve of intense star-producing regions and associated high luminosity, short-lived stars. There's no trace of the orbits that are supposed to form the density wave outside the actual spiral arm. So here's the density wave theory. This is reproduced from Wikipedia. The idea is that orbits are ordinary elliptical orbits, but I don't know why they're elliptical orbits with the center at the middle, but there we are, and that they congregate together to give an appeared spiral. Anyway, let's look at the actual rotation curve. This is, oh God, it's hidden under the It's always the same. The label is hidden under there. I'll get it wrong. It's just my camera and microphone. I'll be, never mind, forget that. Anyway, I can't remember the name of this. It's something like 3028. You can read it. It's the top of the slide there. Okay, that's the galaxy. Now, you've got a straight line roughly through the origin, and you've got a horizontal, more or less horizontal straight line. Now, the 30 kiloparsecs is about 15. No, wait a moment. Yes, it's about 15,000 light years. No. Oh God, I can't remember now. Anyway, 15 kiloparsecs is about the size of a galaxy, a spiral galaxy. This is going way out into the dark region outside, where you don't see much. Here's a whole load of rotation curves. Somebody wrote a paper just giving lots and lots of rotation curves. And they all vary a bit, but you've got this very long straight region going right out. They're asymptotically constant. They're not dropping off like a Keplerian curve would. And here's a close-up of one of the spiral arms in M83, so you can see what it looks like. You've got some dust lanes in there, but you've got the arm, the visible arm, is actually made up of these very bright regions, which are star-producing regions. Short life stars, very, very bright. And no trace of orbits outside that form the density wave. Okay. So galactic rotation curves are so characteristic and simple to describe that there must be some strong structural reason for them. They're very far indeed from the curve obtained with a standard Keplerian model, in other words, using Newton's theory of Newtonian mechanics. Under any reasonable mass distribution, in a Keplerian model, suppose that the mass within radius r of the center is m of r, then equating centrifugal force with gravitational attraction gives you v squared over r. It's g, that's Newton's gravitational constant. Mass inside r over r squared. In other words, mass, if v is asymptotically constant, then mass inside r is asymptotically equal to a constant times r and tends to infinity with r. But we've just seen that r can go very, very large. So it's just a huge mass needed. Nevertheless, in spite of the huge mass needed, the Keplerian model is exactly what is assumed in current cosmological theory. To square the circle, current theory hypothesizes the existence of a huge amount of matter. Since it's not observed, it's called dark. It needs to be distributed in precisely the right way to make the Keplerian rotation fit the rotation curve. Extremely implausible for several reasons. Firstly, it's just been seen that the quantity of matter is huge and tends to infinity with the radius of fit, which, as mentioned above, appears to be unbounded. Second, it's unreasonable to suppose that exactly the right distribution of dark matter happened by condensation for every galaxy. And thirdly, the final arrangement with most of the matter on the outside is dynamically unstable. For stability in a rotating system such as the solar system or Saturn's disks, there must be a strong central mass to hold it together. Failing this, the system will tend to condense into smaller systems. Finally, despite the best efforts expended in the search, nor hair nor hide of dark matter has been found to date. Okay, so I'm going to give you a way of getting a flat rotation curve without using dark matter. And I'm using something called inertial drag. Every dynamical system has local inertial frames in which there's no rotation or acceleration. Newton just has one frame and it's all inertial. So I think the special relativity, general relativity has inertial frames built in as one of the axioms. Anyway, the point is that a mass moving can drag the inertial frames of things that are close to it. And Dennis Sharma wrote his thesis on trying to get Mach's principle to work with a principle where he had masses contributing to the inertial frame at 1/r distance. So in particular, we're interested in its rotation, because that's what's going to get the rotation curve right. So this is the weak Sharma principle, and it's part of his thesis. A mass m at distance r from a point P rotating with an angular velocity omega contributes to rotation km omega over r, the inertial frame at P, where k is a constant. So the basic assumption that I'm making is that the center of every galaxy contains a heavy rotating mass, presumably a black hole, and it's the inertial drag effects from this mass that cause equatorial orbits to exhibit the characteristic rotation curve. However, the analysis applies to any axially symmetrical rotating body which does not need to be assumed heavy. Okay, so we're going to try and get the rotation curve analytically from that assumption. I should say that what Sharma actually does is he uses an approximation to general relativity known as gravitomagnetism. And in that approximation, you do get inertial dragging effect dropping off at 1/r. It doesn't work in general relativity, so I won't have time to explain why. We're just going to take this as an axiom and try and get the rotation. So to fix notation, consider a central mass capital M at the origin in 3 space, which is rotating in the right-hand sense about the z-axis, in other words, counterclockwise when viewed from above, with angular velocity omega naught. Assume a flat background space-time away from M with sufficient fixed masses at large distances to establish a non-rotating inertial frame near the origin if the effect of M is ignored. Let P be a point in the equatorial plane, the xy plane, at distance r from the origin. Rotation of the inertial frame at P is given by adding to the contribution from M the contribution from distant masses, which I've said is 0. The inertial frame is rotating coherently with the rotation of M by the average of omega naught, weighted km over r, because that's what comes in the Sharma principle, and 0 for the fixed masses, distant fixed masses, weighted c, say. Now, if you just divide through by c and normalize by dividing through by c, then c comes out to be 1, and that just has the same effect as replacing k over c by k. So it just leaves you one constant k to determine by experimental theory. The net effect is the rotation km over r times omega naught plus 1 for the distant masses times naught for the no rotation over the sum of those two things, km over r plus 1, and that comes out to a over r plus k, where k is km, little km, and a is k omega naught. Now, Sharma did talk about the general principle where you add up for all rotations, in fact for all accelerations, and then the weighting constants, that this constant k actually is 1 if you use the full Sharma principle. And there's some evidence for it, and it's repeated somewhere in Mrs. Thorne and Wheeler, but I don't want to find the reference right now. Okay, we have to understand the way that inertial drag field we just derived affects the dynamics of particles moving near the origin. Assume that the inertial frame at distance p from the origin, distance r from the origin at p, is rotating with respect to background with an angular velocity omega of r counterclockwise. When computing rotation curves, the formula we just found for omega r, that's a over r plus k, will be used, but for the present discussion, it's just as easy to assume a general function. The inertial frame at P can be identified with the background space, but it's important to remember that it is rotating. There's no sensible meaning to center rotation for an inertial frame. Two rotations which have the same angular velocity but different centers differ by uniform linear motion, and inertial frames are only defined up to uniform linear motion. So for simplicity, you can assume that all the rotations have center at the origin. Then the inertial frames can be pictured as layered transparent sheets, each comprising the same point set, but with each one rotating at a different angular velocity about the origin. Each sheet corresponds to a particular value of R. I've got another misprint there. Okay, we've got to be very clear about what's happening in one of these frames. A particle moving with the frame, in other words, stationary in that frame, has no inertial velocity, and its velocity is called rotational. So you're in the frame, but it looks as though it feels as though you're not rotating in the frame. From the outside, it looks as though you're rotating. From inside, it doesn't. In general, if a particle has velocity v, measured in the background space, then v is v rot plus v inert, where v rot is the rotational velocity we just described, and v inert is the rotation in the inertial frame. So v rot, of course, is r omega r directed along the tangent, because that's how it's rotating. Inertial velocity corresponds to the usual Newtonian concepts, centrifugal force and conservation of angular momentum. Okay, now as a particle moves in the equatorial plane, it moves between sheets. So the rotation about the origin, rotational in one sheet, becomes partially inertial in a nearby sheet. So think like this. Suppose you've got omega r as a decreasing function of r, so the rotation of inertial frames is decreasing as you go out. A particle moving away from the origin and at the same time rotating counterclockwise about the origin, it will appear to be rotating by the sheet that it's in, and this, as you move out of it, causes a tangential acceleration. This acceleration, called the Slingshot Effect, because of the analogy with the familiar effect releasing an object swinging on a string. But at the same time, the particle is moving to a sheet where the rotation due to inertial drag is decreased. And hence, part of the tangential velocity becomes inertial and is affected by conservation of angular momentum, which tends to decrease the angular velocity. These two effects balance each other out in the limit, and this explains the flat asymptotic behavior. So here it is analytically. So let's v with the tangential velocity in the direction of omega. Slingshot effect causes an acceleration dv by dr equals omega of r. Conservation of angular momentum operates on the inertial part of v, that's v minus r omega r, and causes a deceleration, v minus omega r over r, or an acceleration dv by dr equals omega r minus v over r. And adding the two effects, we get this, what I call the fundamental relation between v and r. dv by dr is 2 omega minus v over r. Given omega as a function of r, you can solve this to give v as a function of r. Rewrite it as r dv by dr plus v equals 2 omega r. The left-hand side is d by dr of rv, and so you can integrate, and the general solution is v equals 1 over r integral 2 omega r dr plus a constant. Okay, so now you can get any differential rotation curve you like by making a suitable choice of continuous omega. Now we're interested in ones where v comes out to be asymptotically constant. So in order for v to be asymptotically constant, this integral has to become asymptotically a constant times r. But we've got omega r in there, and if we're not careful, we'll get r squared. So we better put 1 over r with omega. Then we integrate it, we'll get an r. So you're going to get what you want, provided omega drops off like 1 over r, which I said is what we really wanted, the Sharma effect. Okay, so I've just said this. Interest here are solutions which are like observed rotation curves are asymptotically constant, and this happens precisely when integral 2 omega r dr is asymptotically equal to qr for some constant q, and that happens precisely when 2 omega is asymptotically equal to q over r. So equatorial geodesics have tangential velocity asymptotically equal to constant q if and only if omega is asymptotically equal to a over r, where q is 2a. So using Sharma's principle, that's what happens. Okay, now let's specialize the case omega equals A over R plus K, which is the value of the inertial drag we found using Sharma's principle. So substituting in there, V is 1 over R, this blah, blah integral, and you can integrate and there it is. So that's the rotation curve. Now, C is a constant, depends on initial conditions. For a particle ejected from the origin, from the center, with V equal R omega R for R small, C is 0. And for general initial conditions, there's a contribution C over R to V, which does not affect the behavior for the large R. The large R, you're going to get 2A. So the solution with C equals 0, they're two asymptotes. They're like that Begerman curve. I didn't say it was Begerman, but the one I did first when I couldn't read the name of the galaxy. For R small, V is about R omega R, and the curve is roughly a straight line through the origin. For R large, the curve approaches the horizontal line, V equals 2A. Okay, so here's a lot of orbits, rotation curves plotted using this formula with different values of the constants. Now, the axes are now in light years. So 50,000 light years is about 15 kiloparsecs, about half the size we were looking at before. But that's the diameter of a typical galaxy, the visible diameter. In fact, when you actually get into it, you realize there's a lot of dark stuff further out, and that's all rotating. It's all getting the same rotation curve. I did this to try and get a thing that looked like the, I haven't got it here, no. Okay, go back a long way, sorry. I should have it so I can click straight back. Very bad, there we are. I was trying to get something that looked like this. Well, it's not bad. I'm cutting off there at 15 kiloparsecs. There it is. Okay, now, I don't know whether you want me to carry on. What I've done is I didn't do this last time I gave the talk, but I was only giving an hour talk instead of an hour and a half, but we're not getting an hour and a half. Anyway, I'll just quickly go through the next bit. So while we've got the analysis up, we can actually get the spiral structure as well. So analysis is given will be extended to find equations for orbits in general, not just the tangential velocity, and using a hypothesized central generator, the spiral arm structure will be modeled as well. The basic idea, let's see if this light will work a bit more. The basic idea is that central mass accretes a belt of matter which develops instability and explodes, feeding roots of arms. Stars are formed by condensation in the arms and move outwards as they develop. Typical stars on a long outward orbit, and the rotation curves observed for stars in the spiral arm is formed of many such similar orbits. But you don't need that picture to get the horizontal asymptote. Okay, we just found a formula for tangential velocity in an orbit. What we need is a formula for radial velocity, and there are two radial forces on a particle. There's the centrifugal force, and there's the central attraction from the matter. So R double dot is V squared inert over R minus F of R, where that's the effective central force. And just for simplicity, I haven't said it here, but this has come from somewhere I had. We're using a Newtonian approximation, be it M over R squared. So if you stick that in, you get this. So we've got omega is A over R plus K, A is K omega naught, and K is Km. And I'm going to take K to be 1, because there's some, it just makes it simpler, and there's some evidence for it. And we've got that formula for V, and V inert is this, we subtract, sorry about this light flicking on and off, I'll just turn it off. So you get V, R double dot is this, which is that. And then if you multiply by R dot and integrate, it actually is integrable. I did this with an integration package. I didn't do it myself. But half of r dot squared is this big thing, where E is another constant, and this is the energy of the orbit, determined by the energy. From this equation, r dot can be read off in terms of r, and since it's a formula for v, there's also a formula for theta dot, which is v over r, where I'm using r theta for polar coordinates in the equatorial plane. And then you can express theta and t in terms of r's integrals. I couldn't see how to integrate them, but Mathematica is quite happy to integrate them numerically, and it can be used to plot the orbits of particles ejected from the center. And then I've just explained about having these jets coming out from the center. And here's a mathematical plot that comes from that analysis. And I'd like to stress that it's in the correct units. Referees miss this. That's 20,000 light years. This is 40,000 light years. And everything fits with observations. Well, when I saw that, I was stunned because it's so like a typical spiral galaxy. You've got the jets coming out from the center here, condensing into spiral arms. And in fact, you can see that the pitch is getting less as you go out. That's exactly what happens in the model. So it's quite encouraging that the model is roughly, well, that it's possibly correct. Okay, so that's spiral structure.